All right, so we're in example 2 here. We want to know if oat bran lowers cholesterol. And so we're going to do this experiment where we compare oat bran with cornflakes, because maybe however you eat cereal, maybe that lowers cholesterol by itself. Who knows? Maybe the milk that you use when you eat oat bran would lower cholesterol. So we're going to compare oat bran versus cornflakes. So maybe eat them for breakfast, I guess, is what we're doing. And so we're going to take 14 individuals, and we're randomly assign 7 of them to either an oat bran diet or the cornflake diet. So they'll have oat bran for breakfast for 2 weeks, or cornflakes for breakfast for 2 weeks. And then they'll check the cholesterol level. They'll record it as the subject, and then if he was an oat bran guy, we'd have an oat bran number next to him. If he was a cornflake guy, there'd be a cornflake number next to him. All right? You've got the table of those things on your sheet. And this is real data, as far as I know. I think it's real data. And then they swap the treatments. So these 7 that were oat bran, they now become cornflakes people. And the 7 that were cornflakes become oat bran people. So for subject number 5, if he was cornflake the first time, he'd be oat bran the second time. And wait another 2 weeks and wait for the diet to take effect, and then record the cholesterol level again. Okay. So you can see what we're doing here, right? So we would like to just compare oat bran to cornflakes. We could just randomly assign them for 2 weeks, but then we'd be comparing people that had initially different cholesterol levels, so that's no good. So we want to somehow, each person should experience oat bran and cornflakes, like that. And then we're going to randomly assign them because possibly there's some other thing that might happen. If you let them pick which one they wanted, for example, which one did you go with first, maybe the choice that was made would influence the results of the experiment. So we try not to do anything where there'd be some way that something might happen that we don't anticipate. So we're just randomly assigning them either cornflakes or oat bran first. So you could do this same thing just by taking each subject and tossing a coin, more or less the same thing. And then if it's heads, it's cornflakes. If it's tails, it's oat bran. Here we make sure we get 7 of each, and then we flip them. And then for 2 weeks, they're stuck in that diet. And then 2 weeks later, they're in the flip diet, the alternate one. Each time they check their cholesterol. So in theory, the only thing that's different in the first 2-week period and the second 2-week period is the cornflakes and oat bran. It was the only change that happened to those individuals. And we also made the added safety measure of randomly assigning the treatments. We didn't just say put everyone in oat. We wouldn't want to do that. Put everyone oat bran first and everybody. Well, we might think about that. So oat bran for everyone, then cornflakes for everyone. Maybe the cholesterol goes down over the course of the experiment because they know it's being measured and they eat more carefully. So randomly just take 7 of them, put them oat bran, 7 of them put in cornflakes, then follow them forward and swap it. So any of that impact of maybe just being on an experiment that might cause you to be more careful how you eat, it'd be swapped. And so you would see the same random change due to being treated of these 7 oat bran people, these 7 cornflake people as they move forward. And so those 2 things should come out in the wash when we analyze the data. Let's see, I don't know if I answered all the questions. This is, why do you think they were assigned in random order? We certainly want to randomly assign treatments because we don't want them to pick which one comes first and which one comes second. And then why not just randomly assign treatments to one of the 2 diets and record the results? Well, because the people you chose might have different cholesterol levels for the 2 diets. So this way we're using a matched pairs design where the person forms his own pair because he eats the 2 diets. And half of them eat the diet where oat bran came first, and half of them eat the diet where cornflake came first, just in case the order of treatment has something to do with the response. So you would think maybe the oat bran people, there might be some residual effect when they switch to cornflakes. So maybe this cornflake diet here wouldn't have the cholesterol level that it would have ordinarily, but they're doing that to try to eliminate any possible way things could have been messed up and try to just make sure as much as I can it's just the difference in diet, not the difference in the people, because they're the same people, and not the difference between one was first, one was second, because they did that halfway each way. So that should eliminate most of the confounding things that might happen that might cause you to make a conclusion which wasn't really due to the outbrand and cornflakes, but due to some way you set the experiment up poorly. So that seems like a very well-designed experiment. So the design was that, and the data was subject number, their cornflake number, their cholesterol number, and then we take the difference. So you've got the data there. I put the cornflake number in list 1. I put the cholesterol number, the oat-brand cholesterol number in list 2. And then in my calculator, I went list 1 minus list 2, store it in list 3. So that saves us from having to take those differences and tediously do it. We have to enter the values anyway to find the differences, so why not just enter them in lists and then store the difference in a new list. So that's a quick way to get the difference information that you want. So it looks something like that. And then I did a probability plot for the list 3, and it came up reasonably straight. So I'm pretty happy with that. The sample size was 14, so it's not tiny, and it's pretty much a straight line, so everything's cool. And then the hypothesis test we're going to carry out is the null hypothesis of no treatment effect, so oat-brand and cornflakes have the same impact on cholesterol, in other words, none. So you would expect then the cholesterol levels to be the same in the oat-brand and cholesterol sides of the subject's measurements. And so the average difference should be something like 0. And then if oat-brand seemed to work and lower cholesterol, I'd expect the cornflake numbers to be higher than the cholesterol numbers. So when I take these differences, they're mostly positive, and positive enough that I think the mean for the differences is greater than 0. So cornflakes have higher cholesterol is the alternative. All right, so then you go ahead and compute T. I did it in my calculator. We also did it by hand. Here are the values of D bar SD square root of n. There is the mean, the null hypothesis mean, this number here. So we're thinking we want to get evidence against the assumption that there's no difference between the cornflake eaters and the oat-bran eaters in the cholesterol levels. If there was no difference, then these differences on average should be 0. That's what we're saying here. If oat-bran made a difference, we'd expect those differences on average to be greater than 0. And we're trying to show this. So we set up the test statistic, and we're happy to see, if you're an oat-bran eater, that we got 3.34 for T. And then the p-value spit out by the calculator is pretty tiny. So that's less than 0.05. So we'd say over here, our conclusion, reject HO, oat-bran, I think I wrote it over here already, oat-bran lowers cholesterol. And if you wanted to be a little more statistically accurate, it looks like oat-bran, you would say the results observed would almost never happen if the mean of the differences was 0. That tiny p-value is the probability of seeing something that big when the null hypothesis is true. So it's a 0.26% chance. It's pretty tiny, almost never, I would say. I would call it almost never or very rarely. Maybe very rarely might be exactly the right way to do it. Try that instead. Very rarely. That sounds like almost never, but not quite as tiny. Very rarely happen. So since you see that unusual value, you're allowed to reject the null hypothesis and claim that the oat-bran seems to lower the cholesterol level because the assumption that it doesn't. is contradicted by this tiny, the assumption that the mean is 0, as I was saying, is contradicted by this tiny p-value, because that's a chance of seeing this kind of number when that's true. And that is tiny. So if that's unlikely to happen when that's true, then we're going to say that's probably not true. And this kind of value favors the alternative because it's the right tail. And this here is a greater than alternative. So the right tail probability is the p-value, and large values for t favor that alternative, because this says that this is the mean of the differences so much greater than 0 that I get a t-value of 3.3, which is pretty unlikely to happen. And so therefore we can reject the null hypothesis. All right, we made it through that section. That's 11.2. And then on to 11.3. At your leisure, I suppose.